All right, welcome everyone. We are live back with another Vienna.go Golang meetup, this time with a special guest, which is the reason why we had a spontaneous July meetup suddenly. Hi, Bill.
Hello, thanks for having me.
It's a pleasure. Cool. Before we get into why you're most likely here for the awesome talk, just a little bit of housekeeping and intro stuff. As you see the program, you might have seen the program already. You might have seen these streams or this live stream. We are both on YouTube and on Twitch. So if you are not fully aware what this is a Golang programming language meetup with a talk about something very programming specific. So if it's not your cup of tea, it was nice to see. But if it is your cup of tea and you would like to see more of this, then please join us at meetup.com. I'll share a link. That's where we have our community get together, and we normally have these in-person meetups where we get together, listen to a talk or two, and have some normally pizza, other food or drinks, and we can socialize talking about our favorite programming language. Yes, and at the end, I will have mainly time for questions about the talk and the talk topic. But of course, if you have something you want to bring to our attention or discuss, let us know in the chat. In general, we are active on Twitter, not so much now that we don't have so many live meetups to tweet awesome pictures and content from. And you can find us at meetup.com/Vienna.go. So you can join and be notified of upcoming meetups. We don't have specific dates yet for the next semester, but I'm hoping that the first one will be in September. And as always, we need talks. So let us know if you know someone that want to give a talk, or if you would like to give a talk yourself, even if it's just a short 5-minute talk, or you don't have experience before but are curious. I'd gladly help you with some feedback or shape a talk or help you with general advice on what makes a good talk, or just a talk to get you started. That would be awesome. The sponsor is called EBCont, which is also where I work. They are sponsoring my time spent on organizing this meetup. The big thanks to them, and they're also paying for the tool that we're using to stream this live to you. Normally they would pay for pizza and drinks for you if you were in a physical location. We just have to see when we can do that again. And we're also organizing Free Code Camp Vienna, which is a local user group with a meetup format here in Vienna, and also Vue.js Vienna. Yes, just a couple of few words. EBCont, which is an IT services company, are always looking for developers and also other tech roles. Unfortunately, no pure Golang roles. The closest we have is probably DevOps, where you might do some Go in terms of Kubernetes and those kind of things. But our main backend language is Java. If you're looking for something in that line, or even front-end, project manager, business analyst, or you know of someone that are looking in or around Austria, then feel free to have a look or contact me. I'll be happy to give you some feedback. Yeah, and the talk, you might have already written the program. I'm sure Bill will give us a lot of context and information about his topic and talk, so we'll soon get to that. And since I can't promise you any physical drinks or food today, this is the closest we'll get, so feel free to stock up if you have something close by. Then also get it ready and we'll get started. So give me a second. I said I would share with you a link. I think I already shared the link, but just in case, feel free to go to our the place of where we are living and join us, so you get notified of upcoming events. And also, if you are a regular visitor, feel free to leave a review or a comment on this meetup. And even if it tells you to leave a comment, just put something like great, awesome, like one word, so you can leave a star review. That helps others find us more easily. Okay, so I think that was it. Just in terms of more housekeeping, we will keep the questions for the end of the talk, but feel free to write them as we go. That has worked in the previous meetups, and we'll highlight the questions at the end, and we'll get to it then. So without further ado, Bill, the stage is yours.
Yeah, thank you, Rob, for having me. And now would be a good time to drop some of those links
Yeah,
that I gave you. There's 3 links that Rob is about to drop to help you with this talk. One is the GitHub repo with the code that I'm going to share. We'll see that very soon. One is a link to the draft document that I'm going to be focusing on, the current living version of the draft document for generics in Go. And the third link is access to a Google survey that the language team working on generics will have access to. And it's your opportunity to share your thoughts and opinions and to give feedback, not about this talk, but about generics, about the generics and your concerns, your fears, your thoughts, your ideas. We'll talk more about that as we go. So we'll have those 3 links. Now, what I'm going to do is spend just an hour. I'm going to study the clock. I'm in Southern California right now, so it's 9, let's just say 40 a.m., 9:40 a.m. for me. So at 10:40 a.m., at 40 past the next hour, I'm going to stop whatever it is I'm doing, and then we'll get to those questions. But in an hour, I can at least share with you the bulk of that draft document, and that's my goal. The goal of this talk is to teach to the new syntax that is in the draft document so you can have an opportunity to experience this new syntax and then have those thoughts and opinions about whether you like it, whether you still feel like it's Go, and maybe where you would like to potentially change it. This is completely open. There is no version of Go right now that is slated for this release. It's got to be right. But I think if everything goes right, we might be able to see it next year, August release, which would be 117. Maybe we see it in the one, what did I just say? 15, 16, 17, 18, 19 release, heading into 22. This kind of where we are. There's a lot that still has to be done. And all we're focused on right now is fleshing out the syntax for this and validating and verifying that we have an MVP, right? A minimal viable solution that's solving real problems that we can't solve today without this. And I'm going to try to talk to that. And I'm going to express some thoughts and opinions along the way. And then I'll get to those questions at the end. And please feel free to chat and express opinions and thoughts, whether you're on YouTube or Twitch, and have that conversation while I'm talking. Okay, fantastic. So I'm going to go ahead and share my screen right now, and hopefully all of you are seeing the training repo, which was the first link that Rob provided to you. Now, there are 11 examples here. We're not going to have time in 1 hour to get to all of them. My goal is to get through the first 6. I would love to get to 7. We'll see where we are with time. I haven't been that successful in getting to 7 in 1 hour. But the first 6 gives us really the bulk of what I want to share with you in terms of the new syntax, why we need the syntax, and gives you a good feel for the problems that we can solve with generics in this first release. Again, I want you to appreciate that this is just a first release of generics. I mean, there are going to be, once we release this first one, more releases with more feature functionality as it's needed. Now, this is the repo here. There's a README, and the README does have a link to the draft document. I've provided that link as well, or at least Rob did as well. So if you want to read the actual draft, this is it. It's a living document. I'm going to try to give you the bulk of this, like I said. There is also a Go playground that's been provided, and it's constantly up to date with bug fixes and any changes they make to the draft. I won't be using this playground. I'm going to be running the Go tooling on my local machine. One thing that I want to stress when we start is that even what I show you right now today has not been really implemented in the language. What the team has done right now is built a tool called Go, which is a transpiler to transpile the syntax I'm going to show you into Go working syntax so we can compile and build. So this is not currently implemented. It's not in the language. It's just a tool right now, a transpiling tool, so we can play with the syntax, study it, prototype it, learn from it, and improve on it. Now, one of the things I did do is stole this very high-level overview content from the draft. I'm not going to read it, but this is what is currently slated as being as part of first release. This could change. We could identify that there are things here that aren't really needed. We could identify that there are things here that are missing for a first release. We're trying to figure that out. And the only way when I say we, I don't mean the language team. I don't work for Google, don't work on the Go team. When I say we, I mean the community. The only way we're going to really know what needs to be in this first release is if we come together and try to look at the syntax and then take existing code that you have today in personal projects and in work projects and see where generics maybe works. And we'll talk about what that even means. But this is the current high-level overview. I also took the omissions section from the draft. I'm not going to read it, but again, this is currently what is not slated for the first release. It doesn't mean that 2-3 years from now, some of this doesn't get into the language. All I'm saying is that it's not currently being worked on for this first release of generics. And then if you want to run the tooling like I'm going to do locally, there's instructions for downloading the source code, checking out that branch, and then building it. And as you'll see here in my terminal, if I type Go version, you'll see that it doesn't come up as a 1.14 release. It comes up with a development release from code that was checked in earlier today. So we're running that latest version from source, okay? And that's going to have the Go tooling, as you will see. Okay, fantastic. So with all that being said, and with the little time we have right now, it's 40 minutes after the hour. Let me get into this so I can show you as much of this syntax as possible. So one of the things I'd love for you to do while I'm going through this is look at the syntax, study it, ask yourself, does this still look like Go? Does it still feel like Go? Are we making code simpler to read and write? Are we making code more consumable by more developers, not less? This is what we're going to be, these are the things I want you to look at. And we're going to start here with writing a generic function in Go. And one of the things I want to do here as we walk through this code is do it through a progression. Okay, we'll do it through a progression of starting with a concrete version, then looking at how maybe we can make it a little bit more generic in the current version of Go, and then eventually get to the new generics syntax. So with all that being said, here we are on line 13. And you can see here I've wrote a function called print, specifically print numbers. And the idea of this function is to take a slice of integers and be able to iterate using our for range mechanics, do that linear traversal across this slice of integers, and then display individually each integer value in that slice. And you can see here that I'm doing this across 5 lines of code. I've got a label here at the end, at the beginning, got my carriage return line feed, and then we're using our traditional for range loop here to range and print. And if I want to do the same thing now, but work with string values and not integer values, well, I'd have to write another function, right? And this one I called print string on line 21. Instead of taking a slice of int, it takes that slice of string, and it's really the same 5 lines of code minus, some different variable names and a different label. But we can see here that the for range and the print are pretty much identical, right? And if I wanted to do this for floats, well, here I am again. I'll copy and paste this code and change out string for float, right? And that's the general idea, right? That if I'm going to build these concrete versions of code to solve this problem for every unique type that I want to work with, I need another function. Now, one thing I do want to stress here is that from a readability standpoint, from a maintainability standpoint, from what I call a consumption standpoint, I think just about every Go developer at just about every level, even if you're just a couple of weeks in, could look at this code and comprehend what's happening, can read this code, And if there were changes to be made, I think most developers, almost at all levels, could do that as well. And so when we're working with these concrete types like this, we're able to get the best of Go's simplicity and readability in the language. But it can feel tedious to have to continue to copy and paste and write a new function for every unique type of data that we want to print. So then the question becomes, is there an opportunity? Is it possible in the current language spec, let's say version 114 of Go, to maybe make this a little bit more generic? And the answer is yes. We do have some mechanics built into the language. Let's take a look at the function on line 35. Now, I've called this function print assert because we're going to leverage the type assert mechanics that are part of the language to do this. And what I'm going to try to do is write a single function that can output both integers and strings. And we're going to accept that slice of int and or string using the empty interface. The empty interface is an interface in Go that really creates no constraint on the concrete data that we can pass in. But it's going to allow us to write this single function that can accept that slice of int or string. But keeping with the idea that we want to work with the concrete data directly, that int or that string directly, I am going to have to perform a type assertion to know if we're working with a slice of string or int. That type assertion right there on the switch using the generic keyword type then allows me to write case statements to say, well, if it is a slice of integers that was passed through this function through the empty interface, then let's execute this code. If it was a slice of string, then let's execute that code. Now, I wouldn't call this a generic function just yet because it is still constrained to us implementing code for every single case. Essentially, all I've really done, when you think about it, is replaced the two functions that we had right here for two case statements, right? And that's all I've really done. I've consolidated the number of functions we might need with case statements all in one place. If I wanted to work with floats, I will still need to add another case statement. So this isn't really a generic function. It's more of a consolidation of code in one call. Now, the question then is, well, that's fine, Bill, but is there any way to write a generic function to support this operation across any slice in Go today? And the answer is yes, I can write a truly generic function in Go today. And I can do that using the reflect package. So here we are on line 56 with another function. I've called it print reflect. And just like before, we're using the empty interface to accept a slice of any type. The empty interface will allow us to pass data of any type, including a slice of any type. So here we go on line 58. I call value of, using the reflect package, I get a value, a reflect value. And now I can do a test. Well, was the data a slice at all? And if it's not, I can return out. Now, I'm kind of changing the semantics a little bit because I probably should return some error information, which changes the API, but we can get back to that in a second. I can validate at least that we have a slice here. And I can't use the traditional for range, okay, like I was doing before, but I can increment a variable like I and index into each element using, again, reflection APIs. And then I can use this interface method to get to that data, and then we can use the print function to print it. So essentially what I've done is I've gone from 5 lines of code that I said, or I believe strongly, that all Go developers of almost all levels can read, comprehend, and consume, to 8 lines of code with some changes in semantics. And I think we have lost a little bit that ability for all Go developers at any level to consume this code quickly out of the box. I mean, even I had to look up in the Go documentation the certain methods that existed to even write this code. So the code is a little bit more complex. It's taking more lines of code to do and maybe changes the semantics a little bit. But let's be honest here. This is a generic function. I can now pass a slice of float, and I don't have to do anything more to get the output of those floating point numbers. So we have written a using reflection, we have written a generic function. So the question then is there any value in being able to write a generic function here without the need of the empty interface, and therefore without the need of the reflect package, and to be able to work back down to the concrete type to, again, get back to that code that I think more developers can consume at all different levels? And I think the answer to that question is yes. I mean, I think that's something here that would be nice. And this is what this is what this first release of generics is going to be able to provide us. This area right now where we're using the empty interface, like you see on line 56, like you saw before, to write code that's a little bit more generic or fully generic. In this case, without the use of the reflect package, get us back down to the code that we know and love and that we can write when working with that concrete type. So I'm going to show you for the first time now a generic function using the new syntax that's part of that draft that will allow us to get back to those same 5 lines of code and work with any concrete type that we may want to have a slice of or a collection of and print out. And so I want to start here and focus your attention on the 5 lines of code inside this function. And I want you to recognize how they're really identical to the 5 lines of code we started with when we were writing functions specific for a slice of int and or a slice of string. We're back to our label here. We're back to our for range. And one of the things that we're leveraging, if you haven't noticed yet, is the fact that the print function is a generic function thanks to the reflect package. So the print function using reflection is able to output something for a value of any given type. I've been leveraging that. And so you can see here that we're using it again. And it's nice to think. I think it's important to think how Go really does have generics already in a sense because of the reflect package and the empty interface. And that's what print is doing here. So we're back to the 5 lines of code writing this function, but there's some new syntax here. You're seeing it with the square brackets. And I kind of want to break it down. And the way I want to break it down right now is really just by getting rid of it. So let's just take a look at this function the way it is so we can understand why we need some new syntax in order to make this work. Now, if I were to write the function like this, which is identical to what we saw with int and string, this t, this identifier t, is representing a type. The problem is that with this current syntax, the way I've written the code, the compiler is expecting that we or someone is going to define what type t is, right? The compiler in this case is expecting that before we hit that run button, that build button, that compile button, that t is going to be defined somewhere in some source code file. And the thing here is that this is not true in this case. What we want to have the ability to do is tell the compiler that type t needs to be determined at compile time and will not be defined in any source code file before we try to compile, build, and run this code. We need a new syntax that gives the compiler a heads up that t is a type to be determined at compile time, and don't expect us to define what this is, let's say, explicitly in code like I just showed you. So now this opens the door to some new syntax. How do we tell the compiler that t is some type, some concrete type to be determined at compile time? Well, in the current draft, one option is to use square brackets right in this location, use the keyword type, and then list out the name that you want to use for this type to be determined at compile time. The name of the type can be anything you want. You could use a single letter like I'm using, which I like using for slices. I think it helps to think of this as a slice of some type t. But you can use full words here, right? I can use a capital T type if I wanted to and apply that across the board. I can use larger words, smaller words, lowercase letters in the beginning or not. You're going to see me throughout this talk work with just a single letter because most of what I'm going to show you are examples of these kind of collection types of slice. And I think it works well, and it's got some history behind it with other languages. So ideally, what I'm doing is I'm applying some syntax in front or after the function name and before the parameter list here to tell the compiler that this type T is not a type that I'm going to be defining, nor should you expect to find its definition anywhere in source code. But that T is a type, it's going to be a generic type, a type to be determined somehow, some way at compile time. And we're going to use this syntax here with the square brackets. Now, the spec also allows us to use parentheses, and it was actually the first choice when the draft came out. But just a couple of weeks ago, the use of the square brackets now came in, and I'm going to use the square brackets because I think it's going to help with readability. Now, there are a lot of people who are asking for the traditional angle brackets. What I'm going to say to you right now is that this is not an option because it will break backwards compatibility with the language. And if you want to learn more about why, go to my blog on Arden Labs. And if you go to the blog site on Arden Labs, I've got a blog post here at the very beginning, basic syntax. And I explain at the very bottom, very bottom, why angle brackets are not going to work. I'm not going to spend time here going through it, but the documentation for that is here. And ideally, the problem is that we're going to be breaking backwards compatibility with the language. So if you want to know more, please jump on that blog post. It's all there, ardenlabs.com/blog. Okay, get back to our code. So it is this square bracket that's going to allow us to define a type list of identifiers that represent generic types to be determined at compile time and not defined by the programmer anywhere at any time. Okay, brilliant. But because T represents this concrete type, it could represent an int, it could represent a string, it could represent a float, it could represent a user. Because it represents a concrete type, we get back to being able to write code like we did when we were using that concrete type and reduce or eliminate the complexity needed for the empty interface and the reflection package. And I think there's a huge win here in many cases where we're using the empty interface and reflection where it would be nicer and simpler and more readable to work with the concrete type. Now, I love the reflect package. Do not get me wrong. I think the reflect package is very useful, especially when we're writing marshalling kind of code, decoding, encoding, decoding types of calls. I think data validation on like structs, reflection is huge, right? And I'm not ever going to suggest we're getting rid of reflection. What I'm saying is there are times where we're using the empty interface and reflection where we could simplify the code if we could just represent a generic type like T and then determine what that is at compile time. Okay, great. So I want to run this program. So let me go ahead and show you the main function here. And in the main function, we've got that slice of int. I've got that slice of string. I'm doing those constructions. And one of the things I really wanted to stress here was how we are passing that slice as that full slice to all 4 functions that I've implemented. Now, I come back to the terminal window here, and we go into the basic example. We can go ahead and run this code. Now, again, generics has not been implemented inside the compiler yet. There's questions still around that. But we do have a tool, Go tool, called Go, which is going to now transpile the Go code I wrote into Go code that the current compiler can build and run. So I'm going to use the run command here, and I'm going to specify the file that I've been using. one thing I want you to recognize is that the name of the source code file there is a go_to. So the go transpiler is looking for that go_to file to do the transpiling. So if I build now, if I run this through the go tooling, you can see here that the code got built, it got run, and we see our integers and our strings being displayed. And the big thing here now is the generic side of it, right? So the idea is, can I now create, let's say, a slice of floats, float 64, convert these into floating point numbers, right? There we are. And then, without having to write any more code, display this list like we did with the ints and the strings. Now, can't use print numbers or print strings. Again, I'd have to write a new function. I cannot use print assert because I don't have the case statements. But, I can pass this slice of floats to the reflect function because it is a generic function. It will handle it. And I can pass the floats to my generic function because that's what we're trying to accomplish here with the function itself. So if I add this code and we come back and try to run it again, we now see that I'm able to print out these floating point numbers. And I didn't have to write another version of code to do that. And I was able to simplify the code using our print generic function. Now, one thing I want to stress here is that when we look at this syntax where we're trying to tell the compiler T is a generic type to be determined at compile time, don't expect us to define it. It does represent a list of types that we could, if we needed to or wanted to, explicitly define. What we're seeing right now on the call to print generic in these three cases, 90, 94, and 100, is the ability of the compiler to infer what type T is. However, I don't have to necessarily have the compiler do the inference here. I can do this. I can say, okay, compiler, look, I'm going to pass that type for T in at the call site. So I'm going to pass that int. I'm going to pass or tell you that T is going to be an int. I'm going to tell you that T is going to be a float. I'm going to tell you that T is going to be a string. And so that we have this syntax to tell the compiler that these type identifiers are to be determined at compile time. It also acts like a parameter list that we can leverage or use to pass type information in this particular case, on the call site. But with that being said, we don't really want to have usability issues like this. To me, this is a potential usability issue and readability. We want to call these functions no differently than the way we call all other functions today. So what's nice here is that when we pass the slice of integers through, the compiler can see that for the first parameter, we were talking about slice of some type T. You can see that the slice of integers are being passed for this position, and then it can make the inference, right? It can infer that T then must be an int, and we now do everything with integers. So that's really, really nice. That's really nice. So at this point, what I've shown you is a generic function using the current syntax from the draft document and showing you how we're able to reduce some code complexity by no longer having to need the use of the empty interface and the reflect package, being able to write a generic function for some type T, which would be a concrete type to be determined at compile time, and get back to writing code the way we did for that slice of int, for that slice of string. Nice, nice, nice. So we're seeing some benefits of this generic support, and you're getting to see now some of the syntax choices that are currently available to you in the draft. Okay, fantastic. So I've shown you this, but let's move on, because it's one thing right now to be able to write these generic functions, and I promise we'll get back to it. But any real world application that we write will require us to define data types. And it is going to be important that we can define data types with some generics built into it, right? Maybe not the entire type would be generic, maybe with a struct parts of it would be generic, but we need the ability to apply these concepts of generics into user-defined or name types that we're going to be defining for the applications and the problems that we're trying to solve. So let's explore that for a little bit here. Now, let's start with this code right here. And we're going to go through the same kind of progression because I think it helps us to recognize the need, recognize where it's adding value, and then better understand the syntax. So on line 11, I'm defining a user-defined type, my type, a name type called vector int. And this type is based on a slice of integers. We can consider this slice of int the underlying type for the name type vector int. And then one of the things I did, because it's a vector, is I want to be able to push values into the vector. So I added a method named push, and I'm using my value semantic mutation mechanics, right? Push gets its own copy of the vector, appends a new value into it, and then returns the new modified version of the vector. It's really the same API mechanics that append is using, these value semantic mutation APIs, right? And now we can pass individual integer, that's specific integer, into push, and we can make sure that it gets into this vector cleanly. Now, if I wanted to write a vector that worked with strings, now what are we doing again? Pretty much copying and pasting the same code, but we're changing out int for string everywhere. So now I got my vector string, which is a slice of string. My push method uses the same value semantic mutation API, but it has to accept a string, not an int. That's what we're going to put in there. And then we can use append again to do that. And once again, if I wanted to do this with floats, new type, underlying type, slice of floats, new push, accept a float, yeah, got it. Now, one of the things that's happening here that's allowing the push method to be only a couple lines of code, and really these two lines of code to be the same, is the fact that append is a built-in function in Go that is really already a generic function in and of itself. In fact, all of the built-in functions in Go we can consider generic functions. Once again, you're kind of hearing me say that Go already has generics. It has generics through the use of the empty interface and reflection. It has a whole set of generic built-in functions that we have access to, like append, make, new, length, like it's there. And I'm using append here because append can accept a slice of any type and a value of the same type and then perform that operation. Now, even though I'm making an argument that append is a generic function and Go has generics, one thing about these generic built-in functions is that the mechanics that the language team gets to use to write these functions are not extended to us. So though it is fair to say Go has generics, it's just that the way these functions, these generic functions are built, we can't use the same mechanics to write generic functions ourselves. We're limited to just the empty interface and reflection today. But I'm leveraging the fact that this is a generic function to do what I'm doing. Okay, let's go back through the same progression, because if I wanted to use a slice of float, I'd have to write more code. Is there a way to do this in a more generic way in the current version of Go? The answer is yes, and we get back to the empty interface. There it is again. I'm going to write a vector using the empty interface, and you can see that push on line 34 for the empty interface is, again, pretty identical to the push method on line 20. The only difference is it's not a string, it's an empty interface. Now, unfortunately, though the implementation of push and the vector interface is equal in terms of the complexity and the same amount of code, push here, or this vector, really has a different semantic, which is going to cause usability issues on the other side. What is that change in semantic? Well, this vector that I'm defining on line 32, it's not built around just one concrete type. It's not limited to just ints or strings or floats. We can interlace different concrete values inside this vector. Now, you might think, well, Bill, that's awesome. That's positive. And the answer is maybe, but when I iterate over this vector, there's no guarantee what type of data I'm getting out, which now means that I'm back to having to use these type assertions if it's important to know if I'm working with an int or a string or a float or a user. So we're really changing the semantics, which is going to make the usability of this vector harder on the user when data is or potentially can be interlaced. Now let's take a look at a generic version of our vector. And one nice thing about the generic version is that we get to be bound again to a single concrete type t to be defined at compile time, some type t. We're back to the same semantics that we had when we were working with that underlying slice of int or that underlying slice of string. Now, once again, you're going to see me doing this throughout the presentation. I'm going to remove the generic syntax to start so we can look at the syntax in a view that we're more accustomed to. And what I'm really trying to say here again is what? I'd like to define a vector whose underlying type is a slice of some type t to be determined at compile time. And again, I have to tell the compiler that t is this generic type. And we do that again with this syntax. So we're going to use those square brackets again. This time we're binding it not to the right of the function name, but to the right of the type's name. And now this tells the compiler that t is a generic type to be determined at compile time, not a type to be necessarily defined by us. There it is. Now, when it comes to implementing push, we're back to the idea that I want to pass a value of some type t, right? The same type t that's going to be associated with this underlying slice. And if you look at the receiver, we're not just saying vector generic. That's not enough because we still have to represent the idea of t here. So what we're saying here is that we're going to be constructing a vector generic of some type t for the receiver, and we're going to be constructing a vector generic of some type t for the return. And so we need that syntax once again to represent the idea that t is a type to be determined at compile time. And because append is already a generic function, we get to use the same syntax that you see here over and over again. Pretty cool. So you're seeing now how I'm able to define, in this case, a generic vector type of some type t, implement a method push that accepts a value of some type t. And now my vector is back to the same semantics where it's bound to a single value, which makes the usability, I think, simpler and cleaner, as opposed to this interface, empty interface-based vector, which is allowing me to interlace different data. And I want to show you that complexity in the main application. So let's start here with our vector int and vector string. So you see here with vector int, I'm able to push and only push integers into the vector. I'm able to push and only push strings into the vector. And then when I range over this vector, one of the things I'm trying to show you is that even though print is a generic function thanks to reflection, it does have a set of specifiers where you can get very clear about what the concrete data needs to be in the call to print. I'm not using %v here, right? I'm using %d, which means that if I don't pass in a integer, I'm going to get a message at runtime, or my linter will come in and say, Bill, what are you doing? In other words, I'm writing this code in a way so you can see how I have a guarantee that no matter how many values are in this vector, they're always going to be an integer or a %d. No matter how many values are stored in this vector of type string, this is guaranteed to be true. However, let's look at vector interface. I lose that guarantee, don't I? Here you can see me pushing integers and strings. I could very well push floats in here as well. But if I want to get back to the same exact print statements where I'm using %d or %s, I'm back to my type. I'm back to my type assertion to know exactly what the concrete data is. This is the usability issue that I was talking about. Though the implementation of this vector is equal to the implementation of int and string, its usability is not. So this is where the generic vector comes in. I want you to look at this right now. We're pushing just integers. I'm able to say %d. I'm pushing just strings. I'm able to say %s. I don't need the type assertion. But I want you to now look at the construction of this vector. Now, remember when I showed you the generic function call where I could explicitly pass the type information for t, though I didn't need to because the compiler was able to infer the type. I have a situation here with this named type where during construction, there is nothing that the compiler can hang its hat on to be able to infer the type. And so here is a case where I'm going to have to be explicit to the compiler about what type t needs to be during the construction of this vector generic. So here I'm saying, hey, this is going to be a vector generic where t will be of type int, here t will be of type string, and then the compiler knows that the push calls need to be of the same type, t, int, or string. And what's nice now is, again, without any extra writing of implementation, I could define a vector generic where t is now of float 64. I create this new variable here. We can pass in those floating point numbers. Maybe I'll change this variable to f. I can use the specific format specifier for f. And that's it. I don't have to write any more code. I can now use this vector as a vector of the float 64 type. Now, if I come in here and we build it and run it, we transpile it, right? You can see I've got my int, I've got my float, I've got my string. We're not interlacing, and I didn't have to write new implementations manually. The generic version is available and works. Beautiful, beautiful. So the big thing here on this example was that on the declaration of this type in the definition, because the underlying type had to be a slice t, a slice of some type t to be determined compile time, we see the square syntax come back in to tell the compiler that t is going to be defined at compile time, not by us. Treat t as a generic type. And we apply that same t now across the board here for our push method. And then you can see during the construction, we have to be explicit about what type t is going to be. There's no way to infer it. And you can see the construction call now is leveraging the square brackets on the construction. Okay, fantastic. But what if the type that we're defining isn't an underlying type, like this slice of some type t, but we're using struct types to define these generic types? Maybe a field in the struct needs to be a type of some type t to be determined at compile time. And also, how do pointers play into this, the value and pointer semantics that we use quite a bit in the language? Well, let's go ahead and take a look at that by looking at example 3. Now, there's a few things here I want to share with you in example 3, and I'm doing that by kind of creating my own container type, right? I'm going to define the beginnings of a linked list. And I think where this version of the draft is going to be hitting, well, going to use an American analogy, home runs, but I think where we're going to get big wins here is where we're using the empty interface and reflection, where we can simplify some code. I've shown you that. And for these types of maybe container types, like our linked lists or hash maps, these types of things, trees, where we'd like one implementation of this container type to work with all different types of concrete data. This is another big win. That's why I'm showing it to you here. So let's take a look at this, the beginnings of a double linked list implementation. So you can see here that I want to define a node. I'm going to get rid of this. You're going to see me do this throughout the presentation. I think it helps with readability. So I want to define a type name node that works with that stores data based on a value of some type t to be determined at compile time. Here we are again. As soon as I realize that t is going to be a value to be determined at compile time, now we're back to telling the compiler that that is exactly what t is going to be. I want to stress again that we can use anything we want here for the type name. But I think like everything we do in Go from an idiomatic standpoint, we want to use that shortest name possible, but the one that gives us the highest level of context. And this is something that we're going to have to, as a community, define idioms and guidelines around. And right now, for me, that when this single letter, especially T, works, I like using it. There are other examples here as you get later down into the code examples in this repo where I'm not using T anymore, but that's something for you to look at. So here we are again. We want a node in the linked list to store data of some type T, where T will be the generic type. And then you can see the pointer to the next and the previous nodes are now based on a node of some type T. We saw that before. We saw that before in the construction, right? A node of some type T to be determined at compile time. Now the list type again is kind of the value that stores the first and last pointers to the linked list. And remember, nodes have to be of some type T. So now what we're going to say is a list of some type T. So the construction of the list, the type that we use for the construction of the list, then will be applied to the nodes as well. Great. And now just to define a method, I add a method named add to add a new node to the list. And we know that what we need is the data for the node. So you see here, I'm saying, okay, add will accept a value of some type T to be determined at compile time. And that is what we'll store in the linked, or in the node. And you can also see I'm using pointer semantics here, where I'm saying add will accept a pointer to our list of some type T and return a pointer to a node of some type T. So again, it's really the same syntax we have today, but because list isn't complete without identifying that we have in this case, a field name data of some type T, that we're going to apply the generic syntax in these calls. Now, I've got my node defined of some type T. I've got my list defined of some type T. I've got an add method using pointer semantics to add a node with a value of some type T. Let's get a general sense of how this would work. Now, what I'm going to do is not use one of the scalar types. I'm going to use a user-defined type. I'm going to call it user. Incomplete, right? It just has a name. But that's the type of data that we're going to store in our linked list. And I want to show you some things here related to the draft and the syntax. So once again, you see me constructing a list where I have to be explicit about the type. So a list that will store user values in the node. And then you can see now that the add method accepts values of type user. And since I get the values back on the add call, I can display those values. So in this case, T is a value, and we're working with values. But I want you to notice that T is that generic type. And so I can also say, well, in this case, that no, T isn't going to be a value of type user. This time, T is going to represent a pointer of type user, which means that on the add call, T represents a pointer of type user. And we're going to have to do the construction and share the address of each user value in this case. So if I were to run O3 and run it, you'll see that we're getting values and we've got those addresses, right? We're working with values or pointers based on the type of data we're constructing. Now, a question comes up. What if I don't want values to ever be stored? what do I want to lock this in to pointers only? Well, I can do this. I wouldn't make this star t. Remember, this is representing a generic type to be determined at compile time. So this will stay as t. But I could say, hey, you know what? I don't care what t is. A node is always going to use pointer semantics to store it, and therefore add is always going to accept the value of type t as a pointer. I'm now restricting the use of this API to just pointer semantics. I'm not leaving it up to the caller. Now, if I make this change and try to run this code, I'm going to get some compiler messages because it's telling me that I can't do these things now because of the restriction. Essentially now, what I've done to the usability or the caller is told them, okay, tell me what type of value we're working with, which is a user. But remember, we're storing that through pointer semantics, and therefore now add will only accept the address of a user. If I leave the code I commented out, now we're working in double indirection. I said t is a pointer of type user, and you can see the compiler go, well, you're applying another level of indirection here, so what are we going to do? And so at this point, when we're locking in our pointer semantics, remember, this is still of type user, but we're now forcing on the call that we're sharing addresses. So the thing that I want to share here with you is that you have a choice to allow the user to determine if t is a pointer or not by just specifying t here, or locking the user into pointer semantics by applying pointers semantics here. And I'm not going to be able to tell you if one is right or wrong. It's an engineering decision that you're going to have to make. Related to your use case and the problem that you're trying to solve. So this gives the caller the flexibility to determine if they want to use value semantics or not. The other one locks the usability into those pointer semantics. But I wanted to share that with you, and you got to see how this current draft of generics can also help, not just with the empty interface, but with writing these kind of container types that I guess would have to use the empty interface if you wanted to make it generic, but we get to work with that concrete data directly. Okay, it is now 10:30. I told you time would go by really fast. And I really wanted to, I think, end this discussion. I said at 10:40, if I remember. Yeah. So I'm a little bit behind here. I might sneak out a little bit more time. But let me at least share 3 more things with you that are critically important so you can see it in the draft. And let's get back to our functions, because the functions that I was writing before were open to any type of data. But the reality is we're going to start writing functions that eventually are going to require constraints on the different types that we actually can substitute for that generic type t. There's going to be constraints, and we're going to have to define those constraints so everything so we can guarantee at compile time the integrity that we need. So let me share some of that with you right here. So to start, I'm defining a type named user on line 13. I'm defining a type named customer on line 22. And in both cases, these types implement a method named string that return a string. And the idea of this string method is to stringify a user or a customer. And the stringification right now is in JSON, but it could be anything, right? And if I defined another entity type, then I would write another string method that could stringify that. Now, the idea here is I'd like to write some stringify function where, given a slice of users, I can range over those users, call that string method to perform the stringification, and then return a slice of equal length for every user but it is stringified. So that's what the stringified user is doing. Given a slice of user, make a length of some slice string, use our traditional for range, do our linear traversal, make sure you call string against that user, and return that stringified set of users. And if I want to do it with customers, well, it's the exact same 5 lines of code minus the idea that we're working with customers now. So we changed the type out, we changed some variable names out. And if I wanted to do this now with another entity, well, guess what? Got to write another function. So we go back through that progression. Can I do this in a more generic way? And as we already know, yes, Bill, you can use the empty interface, you can perform a type assertion, you can consolidate your functions into case statements, and it's not really a generic function, it's more of a consolidation view using type assertions to get everything into one function call. Fine, but can I write a generic function? Well, I can. I can definitely use the reflect package here. However, if you notice, I just went from 5 lines of code to about, I don't even know, 12? About 12. We went from 5 to 12 lines of code. And I again would argue that those 5 lines of code are consumable by most Go developers across different levels. And this is not. This took me 15 or 20 minutes to write, having to experiment and read through the reflect package APIs. But notice again, it is a generic function. I can validate that it's a slice. If it's not, I can return nil. Maybe that's changing the semantics a little bit. That's OK. But if it is a slice of some type, then I can create that slice of string of the right length. I can't use my for range, but I can iterate over I, and I can index into each index position, and I can test if there's a string method. Remember, the core of this implementation is calling the string method. So I can validate there's a string method. If there isn't, I'm back to maybe a change in semantics, because the other function gives me a guarantee there will be a string method at runtime, because the compiler can. This is all happening at runtime now. But if there is a string method, I can call it in a generic way, get to the data, and then I can get that appended as a string. So in 12 lines of code, I did write a generic version of my stringify function, but the complexity really did go up. It would be so much nicer to be able to write stringify against that concrete type of some type T, get back to my for range, get back to my 5 lines of code, and I can. So I'm going to remove all of this again. And we're going to look just at this function. Now, remember what I'm trying to do here. I'm trying to say, one more time, can I write a function named stringify that works with some slice of type T to be determined at compile time and returns that slice of string using the same 5 lines of code I did for int and string? And I can, if I come back here and write this as a generic function of some type T to be determined at compile time. The problem that I have here, unfortunately, is once again, I need to call the string method. And right now, there is no constraint on T to be of a type where the value would exhibit this behavior of string. Now, this idea of constraint on behavior is not new, right? I mean, I can write a function named Bill that currently leverages interfaces, right? And in this case, I would call this a traditional polymorphic function. What this function does today says that I will accept any concrete piece of data as long as that data exhibits the behavior defined by the interface stringer, which in this case, this fumped stringer interface defines a method named string that returns a string, the same method signature that I've used for user and customer. So we already write traditional polymorphic functions that ask for data based on not what they are, but what they can do, defining the behavior as the constraint. And I have the same situation here. I am calling a method named string on a value of some type T, I have the same responsibility to tell the compiler that this constraint is important, this constraint is needed. And we're going to use the interface here the same way we've been using it in our polymorphic functions here as a way of defining a constraint against the generic type T. Now, I like this aspect of the language because it's not really doing anything new. I'm sorry for a second. It's not doing anything new. We're using the interface pretty much the same way we use it today to define a constraint on behavior. But we need to be able to do that because we are leveraging behavior that we must be constrained on. So you can see here, I've said type T, and then I've added this interface declaration to be able to define the constraint that I need. Really, really nice. So now I'm back to those same 5 lines of code that I had before. Okay, so let me take a look at the application now, and let me see. Let's see this kind of code run. So once again, I'm constructing these slices. There they are, and then I'm passing those slices into the different functions that we wrote here. This is example 4. So let me come back here and go out to example 4, and we'll build this again. And you can see that I'm generating the pretty print strings here of these different functions. Now, I'm not going to go and define another entity. We've already learned that that works. What I want to do here is just remove the constraint for a second and show you what the compiler says. And you can see the compiler says what we would expect it. And it's saying, hey, Bill, on line 114, you're calling a method named string on that value of type T, but you haven't really said that type T needs to be bound to something. So I can't compile this code because there's no guarantee that T will have a method named string. It would be the same thing if we were writing our traditional polymorphic functions and tried to call some method where that method wasn't being used. So in this case, when I come back and I add func.stringer here, now what we're doing is telling the compiler to apply this constraint, and that gives us the guarantee that that value of type T will work. All right, so pretty cool. Now, there's another type of constraint, however, that is very unique to generic functions that we don't really have around our polymorphic functions. And this is something that is now going to be kind of new to the language. It's an area of the spec that we're still kind of looking at and playing with. And I want to share that with you too in this time that we have. So let's start here with line 16. And on line 16, what you see is a function named add. Now let's get back, and you know me, I like to remove this when we're first looking at code here. Look at this function on line 16. You see here that we have an add function, and what I wanted to do was, given a value of type T, v1, and another value of the same type T, v2, add those two values together to form a new value of type T, right? And the operation is needing the ability to use the plus operator, Now, as we know, not all values in Go can use the plus operator, right? If I was getting back to my user and my customer types, well, then I'd have a problem. I can't add 2 users or 2 customers together. We don't have operator overloading in Go. We don't have the ability to write an operator plus method. So we have an interesting problem here because we have to be able to define a constraint around data that we can use with a plus operator. Now, we go back to this syntax again because we want to work with a value of type T, okay? And again, that's not enough. I can only work with types that work with the plus operator. So what the current draft suggests that we do is define a list of types that will be the constraint for this function. And you can see here that what I'm doing is defining an interface with a list of types, in this case, string, the full set of ints, and a float, and saying that this generic function will only work with values of type t that are in this list, So now this is really new syntax, and it's an experiment that we're looking at because this is really a special type of constraint. It's not a constraint, right, that can really work or be applied to our traditional polymorphic functions, because our polymorphic functions are about behavior. Here we're saying I will accept a value of any concrete type that exhibits this behavior. This isn't really about behavior. This is about properties of the data, whether it can, let's say in this particular case, operate within the scope of this plus operator. Now, because it doesn't really apply to our traditional polymorphic functions, and we're leveraging interfaces to do this, this is an area of the spec that even the language team that's working on this has some iffies around. They're like, you know, because we're kind of breaking interfaces for traditional polymorphic functions, maybe this isn't something that we should be doing inside the interface. So this is an area that's still being explored, and an area where maybe it's really not needed in the interface. I don't know yet, but this is something that we're going to be looking at. But we do need to be able to define this type of constraint, because if we can't, then we're going to have problems where maybe some value of type t sneaks in, and then we've got runtime problems. So I want you to see how we're applying a type list in the scope of an interface declaration to add a constraint to type t, where we can guarantee that those values can only be used in those plus operations. And it does truly limit types to these types. Now, that could be applied to an underlying type, okay? So if I define Bill as type int, underlying types can match in these particular cases. Underlying types can match. So be aware of that. Okay, great. So you're seeing that. Now, another aspect of the spec, one idea, is maybe these pre-declared type constraints can be defined. So in this particular case, we've got this pre-declared type constraint called comparable. And it's a way of saying any set of types can be of type t as long as they can be used in this type of statement, okay? And instead of us having to define interfaces around that, they're pre-declared, and then we can leverage them. So you can see here, because we've got v double equals find, where t is a value of some type t in the list, and t, we're going to say only those types that are comparable. And there's one more aspect to this that maybe reduces some complexity. And because of time, I'm going to sneak right over to it. You can, or you do have the ability today to define interfaces that can have a mix of behavioral constraint and type list constraint. And this one's kind of interesting because if we come back to my generic function, I'm defining a function named match that works with a slice of some type t and a value of some type t, where we range over the list of type t. And for each value in the slice, we call the match behavior, passing a value of that type t in, and determine whether the match is true or false. So what that means now is that I want to define t as a slice of some type t. But let's get rid of this for a second. I now have an interface where the behavior has to be a match function where a value of some type t is the input. And so you can see here that we're defining t again as a type to be determined at compile time, and that type being the type used for input into the match. which now allows us to satisfy the behavior here on line 76. And so it's an interesting piece of code because we needed to define behavior based on that generic type T to be determined at compile time. And you can see how we have to also do that at the interface level. Now, the last thing here I'm showing you, and it's not needed here, right? But I wanted to show you that you can define, at least in the current draft, interfaces that provide a type list and behavior. Now, it's not needed here because there's no restrictions on type T that require me to actually list it out. I'm not doing plus operations or equality operations or anything where I have to do a constraint against the type of data that we pass in. And I have a feeling, since I haven't found a practical use for this yet, that maybe this isn't even needed at all. And if it's not needed at all, then maybe that really helps to simplify what we do with these type lists and not necessarily have to put them inside of interfaces. I don't know. As I'm trying to say, this is an area of the spec that we have to kind of study and learn from, and an area of the spec that still needs some work. So if you're looking at this and you're starting to go, Bill, I don't know about this. Well, I mean, you're not alone, and I think, and we have time to look at this, but it's an area of the spec that we do have to study. Okay. It is now over an hour, so I'm going to stop there. I didn't get to number 6. That's fair. That's something you can do on your own. I'm going to stop sharing for a second. Come back here.
Hello.
Yeah.
Thanks for the talk. We'll do some questions. I forgot to introduce you, but I think for most people, you don't need an introduction. Bill is an author. Or I don't know if it's the only book, but one of the books is Go in Action, and also a speaker and a very active person in our community that I think most people associate with Golang. And feel free to add your own plug or anything, Bill.
No, I mean, it's all good. I mean, really, what I say right now is I tried over the last hour to showcase the bulk of the new syntax. I didn't get to a couple things, but I think with what I've given you, you can look at the rest of that on your own. And it's really important to not just me, but to the language team in the community that if you have an interest in generics and it's something that you really feel like you're going to be using and can leverage, then try to take some active part in looking at code today in your projects, code today at work, and working out the syntax, like that last example I showed you, where we have to constrain based on the type of data, right? Not just behavior. There's work there that needs to be done. And so until we experiment and see how much that's even needed, we don't know. There are aspects of the spec, or the draft, I should say, where we just not even know if it's important. We won't know until we look at enough programs. And so your help here is critically needed. And that's why on the links that Rob shared, one of them is that Google survey. And it's really a great opportunity for you to talk, honestly, talk directly to the language team about your thoughts and opinions. If you've got more specific things, if you come up with examples that you think are awesome, send them to me. I'm going to drop my email here, and Rob can share that as well. Yeah. Share me examples that you think are great examples to help with teaching. Show me examples where things aren't working. If you've got direct questions around examples, share them with me. I might even just have to send them to the language team to get them answered. But I want to be that conduit for you to get you answers and to kind of talk about some of the engineering options that we have with this first draft release of generics, hopefully in a year or so.
Yeah. We can take some questions. There's one that's a half question, I think. The chat already commented on it. I wonder if this generics implementation is capable of letting one implement lambda calculus, says Christian.
Don't think so, Christian. I haven't experimented with this yet, but I would love for you to do that and share with me anything that you find. And again, if enough people are saying that this is really needed in a first release, that's something that the language team will absolutely consider getting in there.
Yep.
Yeah.
One thing that is not clear comment, but Horst, feel free to summarize it in a question if you want. But he's commenting more on readability, and I think the main point he made in this comment that he has nothing against generics, but he really thinks its syntax hampers code reliability and it will need some getting used to.
He's absolutely right. The more that I'm using the syntax, the more readable it becomes for me. And if you notice throughout the presentation, I was removing the square brackets and then putting them in. And I tend to write code like that first, even though it's not compiling right away, because when I'm writing the code with the idea that T is some type, then I can read it. And then I put that square bracket in, and then I can kind of almost ignore it. I know it's there. So it does take some time getting used to. And this is the big question and the fear that everybody has, that this is going to get abused, and we're going to see more and more code in the open source or public ecosystem that's going to be less readable, less maintainable. But one of the things I did try to show, at least, or I hope I tried to show, is in areas where we're using the empty interface today, where we're having to do a lot of type assertions, where we're leveraging reflection, and where some usability is hampered because of these things, I think generics can really help. And the end goal, at least for me, is to maybe see a package of concurrency patterns in the standard library. I think we probably have more bugs in the Go ecosystem because of concurrency than maybe anything else. And if we could standardize a lot of the concurrency code that everybody has to write themselves, I mean, that could reduce a lot of bugs, right? And even maybe help with readability. So I'm really excited about some of those aspects of it.
Cool. Thanks.
Yeah.
Christian is having a question that's on another topic. Generic code requires to be resolved during compile time, so I assume those will also always bypass any build cache. Is there any intermediate binary AST form that may keep the quick compile times?
None of these engineering decisions have been made yet because there's a lot of trade-offs here in the actual implementation. To give you an example, okay? The language team could decide that for every unique type to actually create a unique implementation. So for int, for string, for float, actually write a separate function for int, string, and float. That could come with some advantages in performance potentially, but it comes with trade-offs on code bloat, right? Binaries. They could decide to write a single generic function, maybe using some of the mechanics they have today for append, right? To take all three of those generic functions for int, string, and float and still write a generic function underneath, which might also now mean that we lose maybe some of that performance that everybody thinks they're going to get, but your code size is smaller. So your question is excellent, Christian, but we're not at a point to even begin to answer that yet. We're right now just at a point of, do you like the syntax? Does it work for you? Does it solve the problems that we want to solve with generics? And then once that's done, a whole nother can of worms open up.
Yeah.
And how do we actually want to do this the right way? Because all I've shown you is a transpiler. All right, that's all I've shown you. So I have no idea yet. Nobody knows. I'm sure the language team has thought about it a little bit, but there's nothing that's been done there.
We have a follow-up comment, I think, from Horst to syntax. We'll go for that, and then we have another question from Christian. So Horst is commenting that he understands the choice between parentheses and brackets in generic syntax in function signatures is an issue, but neither choice is ideal, in my honest opinion.
And I think at this point, with all of the conversations that I've seen on the mailing list about this, right now the square brackets are the front runner for this. But if you've got other ideas other than angle brackets that haven't really been talked about, please share them with the community, because we want to get this right, and we only have one opportunity to do that.
Good point. Christian's asking, can a generic type be specified for a function that does not use this type in its signature? So I can set a type that this function will require from another function that it calls, like a factory.
If you did, and it's possible, you'll have to explicitly define what type T is on the function call. And I think if you look at my example for the hash map, I have some of that. Okay, so You don't have to use type T as an input and or a return. You can use it inside the function only, but then it's not going to be able to be inferred, and you're going to have to specify what that is. All right. And I think if you look at the hash code, I have some of that in there. So I think it's a great question. Definitely look at that example number 11. And I think you'll see some aspects of that. It's been a while since I even wrote and looked at that code. So it's an excellent question. But I think you just I remember you're going to walk away from any form of inference.
Cool. We'll go through some comments. I think there were some metaphors and stuff here. So in the meantime, if anyone has more questions, feel free to post them now. And I think for the recording, I'll just highlight the different resource links that Bill went through in the beginning. So here's the link for the talk material. So you have it on screen as well. I'm just adding it for accessibility. And then we also had the draft document that we've gone, that's been mentioned. That's this link. And then the Google Share survey that I ended up sharing twice because of the emphasis from Bill. That's also for you to see here. And then should we also share your email, Bill, again?
Share my email. Anybody can just reach out to me directly with questions. Use that playground, the Go playground, to share code. It really helps. And if you come up with interesting examples that I don't have yet, or you run into interesting problems, talk to me. I'm here to help be a conduit to the language team as well, and give you the ability to get access to them outside of the public channels, which, some people like to debate there. I don't. So, but I want everybody in the community to have an opportunity to have a say or express ideas.
Thanks. I think we'll just quickly go over some of the comments. So Christian pointed out quite early that it would be fun if it was in the version 120. You mentioned possible version numbers.
I think it could be in the August release next year, which would be 17, or the release after that in 18. I think it can be, if we could flush out the syntax over the next 6 months. I mean, I don't see why it couldn't. That being said, right, I mean, there's still a lot of work to be done.
Yeah, here was some comments. It's like a 3-comment follow-up. So it seems that generics, yes or no, is in its core topic like chauffeur or airman, was at the beginning of aviation, make aircraft controls flexible and difficult to master, or stable, easier, and less capable. And the disparity also influenced the controls of the Apollo spacecraft. So that's a nice parallel there. Any comments, Bill?
No, but I think it's that this is the engineering decisions and the trade-offs that have to be made here. But I will tell you this, just so there's other contexts. The language team, and at least me, I can't speak for the community, but the language team and myself, I want to see the language grow. I want to see the language being used by more companies. And a lot of survey work over the last couple of years has turned up that some of the bigger enterprise companies out there are not really using Go for core application or service development because it's lacking some of these generics. And that's why I think right now we're at a point where so much work over the last 5 years has been done on performance and stability. And we now have this opportunity to focus some resources on this and see if there's a solution here that can bring in another 1 million developers and in another 1,000 companies that aren't using the language. There's no guarantee that we will. But remember that the language team is about 50 people. That's it. They got enough work for 300 people every day. It's 50. So they have to be incredibly targeted in what they're working on. And it's only now, 10 years later, with 50 people, that 2 or 3 resources can be dedicated to this. All right. But to me, the real goal here, when you look at it from a business perspective, okay, because there's a business here, right, is can we get another 1 million developers using Go? can we help those developers solve problems that they're solving today in other languages? And yes, with that trade-off being keep the language the way it is, keep the things that we love about the language, and how do we balance that? Okay, and
Yeah.
that's where we're at. So everything that Christian said is kind of in that same space, right?
Yeah. Just a comment and a thank you, or just a comment from Zigzag. I find defining type constraints, or rather your type lists in an interface useful. This is so much similar with TypeScript's interfaces. Can't wait to see how generics will be used. And then we have a question from Christian. Bill, I understand you follow the discussions closely. Do you see any trend? Like, yes, this is what's going to be, or fewer features, etc.?
I'm not actually spending a lot of time on the mailing lists and the full levels of discussion. There's so much that goes on there. It's overwhelming. But these are my opinions. Again, I don't work for Google on the language team. I don't know how this is going to fall out at all. But I have a feeling that the square brackets are here to stay. That's what's going to end up being the operator for that list. The other items that I saw with double angle brackets, angle colons, I mean, I don't see that. So I think there's a trend there. As it relates to the constraints that I showed you, I still think there's things that are open there on discussion. One of the things, however, I have asked the language team, and I'll continue to ask the language team, is as we get closer to, let's say this, once we've identified the syntax choices, and now they're ready to actually go ahead on the engineering side of it, what the community needs is a set of idioms, strong idioms, guidelines, and a lot of example code to help guide everyone into what are the best practices for using generics, when should you really be using them, and then everyone, because I don't want to say just teachers, because you can argue that I teach Go, but everybody teaches Go at work, right? You have these teaching moments all the time at work. Maybe I'm coming in and helping a company, but when I leave, there's still teaching moments. And so everybody who's teaching this needs these types of guidelines. So the Go team has been very, very positive in saying that we will provide the idioms, the guidelines, and the example code. And this goes all the way down to how should we name these types? When should we use single letters? Maybe when we should use larger letters. And I think all of this is going to help. A lot of the concerns around abuse is going to help concerns around making sure there's consistency across the board throughout the community.
Cool, thanks. Well, good. Then I think it's mostly any parting words from you, and we got a lot of thanks from the audience in the comments. Thanks from Christian, and thanks from Horst for the presentation, and also from Pablo. Thanks for the talk. I also enjoyed it very much. It is also going to be more powerful to play around with it myself. So you mentioned the playground. People should really get it in their fingers to kind of get a full feel for it, for sure.
Yeah, and look at the rest of my examples. And I'm sorry I didn't get to in that hour more of it, but it's all there. So definitely do that. And please, please, please use the survey, answer it, be a part of the conversation. It's an anonymous survey too, so you're not going to get into these academic debates. And I promise you that the language team is looking at it. They're reading it, and everything that you say is being taken into consideration as a whole. So please, please, please fill that out. And that's it. I really appreciate your time and everybody's time being here. Thank you.
Yeah, thanks a lot for joining. Thanks for giving us this awesome talk. For the audience, just a quick reminder, as I said, we always need speakers. Like, we have a good sponsor, even in these online times, we have a way of getting to you. We have a physical location whenever we need one. Hopefully we can get back to that sooner than later, though in my opinion, I don't think I'm seeing that happening before January, February next year. Really depends how things develop. So we always need speakers. It's also, if you want to help with the meetup, let me know as well. There are different ways of helping. Right now, you can leave a review so other people find it better. And thanks for joining. And hopefully we'll see you again in September, I think latest in October, but we'll announce the dates as soon as we have them ready. So thanks, Bill, and let's
All right.
end the
Bye,
stream.
everybody.
Ciao, bye-bye.